Okay, this is the end of chapter 4, and last time we got together we were talking about redox reactions, balancing redox in acidic and basic solutions. So today we're going to review how we can recognize redox. How do I know that something's redox by just looking at a reaction? We're going to talk about reaction prediction again. We're going to revisit that, and then we're going to do some precipitation reactions that involve stoichiometry. So a simple redox, one way to recognize it, remember these are just clues, is hydrogen displacement. So in this case you have a metal plus water, and that's going to give you a metal hydroxide or a base, and hydrogen gas. So that's one way to recognize redox. Another example of this could simply just be Na solid plus water, and obviously it's going to make a metal hydroxide, so it's going to give us NaOH and H2 gas. Usually the hydrogen displacement is seen with a group 1 or group 2 metal. Here we have metal displacement. This is like a single replacement reaction. Remember that the metal pushing in has got to be more reactive than the metal it is pushing out. And also with metal displacement, we also have halogen displacement. So both of these are single replacement reactions in which either a metal or a halogen, a nonmetal, are displaced. Combustion. Combustion is always redox. So remember, it's basically any organic compound in the presence of sufficient oxygen will produce carbon dioxide and water. Disproportionation, we've already seen this, we just don't usually call it this, but that's the politically correct name, I guess you would say. That's where one substance is both oxidized and reduced, and you'll see this a lot with chlorine. Here chlorine's in the free state, so it starts at 0. Here it's plus 1, because oxygen is minus 2, and then here it's negative 1. So here we have a plus 2 and a plus 1, a negative 2. Here we have a negative 2 and a plus 1, which gives a net negative 1, and here it's negative 1. So Cl went from 0 to Cl plus 1, and it went from Cl0 to Cl minus 1. And then reactions involving Oxxo anions, and that's simply ions containing oxygen, an Oxxo anion. And what we'll see here is that oxygen is negative 2 here, and the chromium is plus 6, and here it goes to plus 3. And then the iron is plus 2 going to plus 3. Here's some redox reaction predictors. If we see these things, it kind of helps us. I don't expect you to memorize these, but it does make it easier if you do know some of them, I guess. So let's just take a look at a couple of them that are highlighted. So if you have H2O2, for example, this is an important oxidizer. What's formed is H2O. Free halogens, this is an easy one to remember. Free halogens that are 0 usually become the ions. Metallic ions, So if you have like Fe plus 3, it would go to Fe plus 2, those type of things. We'll go through some of these and we'll pick them out, and I think that's going to be the easiest way for you to see them. Okay, so let's go back to review some prediction reaction with redox. So we've got solid copper. So we have Cu plus dilute nitric acid. Well, as soon as you see nitric acid, you should be thinking strong. So right away, you know that this is going to dissociate into this. It's a strong acid with 100% dissociation. So I'm going to write it like that. And what is that going to do? Well, first of all, metals are probably going to be oxidized, so this is going to go to Cu plus. But if we look back on our sheet there, I saw something about NO3 minus, so let's just look back a minute. Here's dilute nitric acid, and it's going to form nitrogen monoxide. So there it is right there. So this is going to be plus NO. So that's basically what's happening there. That's what we're concerned about. We're concerned about the Cu going to the Cu, oops, that should have been a plus 2, I'm sorry, and the NO3 minus going to NO. A solution of potassium permanganate. So we've got KMnO4, and I know that this is going to be involved as soon as I see the manganate ion is mixed with an alkaline solution of sodium sulfite. So we've got sodium sulfite, Na is plus 1, sulfite is minus 2, so Na2SO3. So let's go back to our list. Let's look at our list and see what's going on. MnO4 in a basic solution goes to MnO2. So alkaline tells us it was basic. So this is going to go to MnO2. And do we have anything about the Na or the SO3? Let's go back. Sulfite ions turn into sulfate. So that would be very helpful. Sulfite is going to turn into sulfate. So basically you have the KMnO4 turning into the Mn plus MnO2 and the Na2SO3. It's the SO3 turning into the SO4. Ethanol burned in air. Ethanol, eth means 2, so it's a 2-carbon alcohol, so that's C2H5OH plus oxygen is basically going to produce CO2 and water. You just have to know that one. And this would be 2, 3. We need a 3 here because we've got 5 and 1 is 6 H's, 6 H's, and we've got 3 oxygens here, times plus 4 is 7, 6, and 1 is 7. Okay. Sodium metal, Na, in water. Remember, group 1 or group 2 in water is going to produce a metal hydroxide. So this is going to be what I showed you, the NaOH plus H2 gas. And hydrogen peroxide solution added to a solution of iron 2 sulfite. So we've got H2O2 plus Fe sulfate, FeSO4. There we go. Now, a couple of things are going on here. We know that the Fe plus 2 is going to go to Fe plus 3, but there's something going on with the hydrogen peroxide. Now, there's two things that can happen. You can have hydrogen peroxide acting as an oxidizer, producing water, or hydrogen peroxide acting as a reducer and producing oxygen gas here. Well, you had the Fe plus 2 going to Fe plus 3, so we already have something reduced, so that means that we need to have something oxidized. That would then produce H2O. So basically, you've got the FeSO4 going to the Fe, and you've got the H2O2 going to the H2O. And then, we'd have to balance this, obviously. You've got Fe plus 2 going to Fe plus 3. You'd balance with 1 electrons, and then we'd have to go through the whole gamut. But this is just basically to help you predict what's going to happen and to recognize redox. Let's do some stoichiometry with precipitation reactions or redox reactions. So here we're starting with 10 mils of 0.25 barium chloride, and it's reacted with 10 mils of 0.35 sodium sulfate. So the first thing we have to do is write a balanced reaction. So we've got BaCl2 plus Na2SO4. And this should be a double replacement reaction, so we've got BaSO4 plus NaCl. And we need a 2 here. And everything else looks good. So let's write down what we know. We've got 10 mils times 0.25 molar. And that's going to give us 2.5 millimoles. Remember, when we take milliliters times moles, we get millimoles. And then we've got 10 milliliters times 0.35 molar, and that's going to give me 3.5 millimoles. So we are going to figure out how many grams of precipitate will form. Well, first of all, we have to basically figure out what our limiting reagent is. And in this case, I know what it is because these are at a 1-to-1 ratio and there's less of the barium chloride than there is the sodium sulfate. So starting with my millimoles, 2.5 millimoles of BaCl2, we know that 1 millimole, and you don't have to do it like this, you can turn it into grams if you want to, is going to be 233 milligrams. So basically, when I take and multiply these, I'm going to get my millimoles cancel. I'm going to be left with milligrams, which is going to be 583 milligrams, or 0.583 grams. What are the concentrations of all ions present? So now they want you to use what's called a BCA table, which is going to be new. BCA is before, change, after table. So how we do this is we write what we have, BaCl2, and basically it was plus the sodium sulfate, and that yielded BaSO4. So I'm going to look at this strictly from the point of what I had before, what was my change, and what was my after. So I started with 2.5 millimoles of the BaCl2, we figured that out, and Na2SO4 was 3.5, and initially we didn't have any product formed yet. As the reaction proceeded, we used all of my BaCl2, as it was my limiting reagent, and I must have formed BaSO4 via the reaction. So afterwards, there isn't going to be any limiting reagent left. I will have 1 millimole in excess of the Na2SO4, and I will have formed 2.5 millimoles of barium sulfate. So what's the concentration of the ions? Well, BaCl2 concentration is equal to 0. Whenever we do square brackets, that means concentration. Na2SO4 concentration is, we have to separate this out. So within this you've got Na, and there's actually really two NAs. So you have two Na plus in here, and you also have one SO4 2 minus. So let's take this, so the SO4 2 minus, now we had 1 mil left, so 1 mil concentration is moles over volume, right? So I've got 1 millimole divided by my volume, which is 20, because I believe they said that we were starting with 10 each, 10 mils each, 10 and 10 is 20. So 1 divided by 20 milliliters, so this is millimoles divided by milliliters, which is going to give me 0.05 molar. The Na does not participate at all in this reaction, it's a spectator. So originally we had 3.5 millimoles of the Na, but there's 2. So it's 2 times 3.5 millimoles, which is going to give me 7 millimoles. But we have to divide that by the total volume, which is 20. And we get a concentration of 0.35 molar. And this is for the Na, all of that. And lastly, chlorine, concentration of chlorine. Well, chlorine was a spectator as well. And for chlorine, we had an original concentration of 2.5, but there is 2 Cl minus. So the concentration of chlorine is going to be 5 millimoles divided by 20 milliliters, which will give me 50 mils of 0.1 molar sodium phosphates mixed with 50 mils of 0.1 copper 2 chloride. So sodium phosphate, Na3PO4 plus CuCl2, which is going to give me NaCl and Cu3PO4 2. Okay, so when we balance this equation, we're going to wind up with 2, 3, 6, and that's it. So we've got 6Na, 6Na, 2PO4, 2PO4, 3 copper, 3 copper. 3 times 2 is 6Cl, and 6Cl. And we've got the same amount of both. We've got 50 mils and 0.1 molar, which is going to give us 5 millimoles. And we've got 50 mils of 0.1 molar, which is also 5 millimoles. Now you can look at this intuitively. This has a coefficient of 2, and this has a coefficient of 3. So if we were to determine what our limiting reagent were, given that we have equal millimoles to start with, we can tell right away that Lr, the limiting reagent, will be the copper chloride. So let's figure out, they're asking us how many grams of precipitate will form. Well, we need to know how many millimoles we're going to have, and then they're going to ask us the concentrations of all the ions present. So they're going to want us to use the before change after table. So I'm going to set that up already on the side here. So I've got Na3PO4 plus CuCl2, and we're making NaCl and Cu3PO4 2. And I didn't put the coefficients in over here just because I'm just trying to figure it out what I have. So we're starting with 5 millimoles, 5 millimoles, and we're starting with 0 and 0 to begin with. Now, in order to figure out how much of this we're going to use, we know we're going to use all of the CuCl2, and this is going to be 0. Right away, I know that my concentration of Cu ions at the end is going to be 0, because all of that is going to combine with the PO4 to make the solid precipitate, which I should have put in. NaCl is aqueous, so they're going to be floating in solution. What I need to know is how much of the PO4 am I going to need to combine with the 5 millimoles of Cu to combine the precipitate. So I'm going to do some mini stoichiometry up here in the corner. I've got 5 millimoles of CuCl2, and I want to know how much I'm going to use. So in my balanced equation, I have 3 CuCl2, and I have 2 Na3PO4, and these are moles. So that's going to cancel with the moles, and I have 2 moles here. So I'm going to times 5 milli by moles, and I'm going to get millimoles again, but I got to divide by 3. So 5 times 2 is 10, divided by 3. This is going to give me 3 millimoles of the Na3PO4. So I'm using some mini stoi up here. Not 3, sorry, 3.33. This is repeating. So this is going to be minus 3.33 here, which is going to leave me with 1.67 millimoles. Which means that when these dissociate into their ions and the PO4 combines with the Cl2, I'm going to use 3.3 millimoles of the PO4 ions to combine with the 5 millimoles of Cu ions. And that means that there'll be 1.67 millimoles remaining of the PO4 3 minus. That's what's going to remain. It's going to be left unused. We said over here that there'll be 0 millimoles of the Cu ions. And what will happen over here, plus 1.67 millimoles. Now, we didn't use any of the NaCl. NaCl is aqueous, it's floating in solution. All right, let's go with the grams of precipitate formed. We know that we formed 1.67 millimoles of Cu2PO4 3. And just in case some of you don't realize how I did that, I did it the same way that I did this in the upper left-hand corner. The way that I figured out, using the limiting reagent, how much Na3PO4 I would use, I can also use mini Stoi to do the same thing. So if I have 5 millimoles of CuCl2, that's my limiting reagent, and I have 3 millimoles of CuCl2 in my equation, and I'm forming 1 millimole of Cu3PO42. So basically 5 divided by 3 is 1.67, and that's how I got that over here. So we can do this 1.67 here, which means that the net is 1.67. And I could technically do the same for NaCl. If I have 5 millimoles of CuCl2, 3 on the bottom here for the CuCl2, going to 6 Na. So 5 times 6 is 30 divided by 3. Oh, this would be 10. This would be 10 millimoles. Guess I should have done the math. So I'll show that up here. So this was 5 millimoles of the CuCl2, and we have 3 CuCl2 going to 6 NaCl. 5 times 6 is 30, divided by 3 is 10. So this is going to be plus 10, and this will give us a net plus 10 at the bottom. We're not there yet. I just realized my math was wrong. So back to figuring out grams of precipitate. We have 1.67 millimoles. That's how we got that right there. And we know that 1 mole of Cu3PO42 has a mass of, I got 380.5 grams Cu3PO42. Hopefully my math is right on that. Somebody might want to check it. So what that is going to give us, moles cancel, it's going to give us mg, it's going to give us milligrams, which is equivalent to 635 milligrams, or 0.635 grams of the Cu3PO42. Okay. Now they want to know what are the concentrations of all the ions present. So remember, molarity equals moles over liters. And let's start with stuff that we know. First of all, first and foremost, we know that the concentration of Cu2 plus is going to be equal to 0 because we used it all. And we know that there are 1.67 millimoles of PO4 remaining that we did not use. So PO4 minus is equal to, so we've got 1.67 millimoles over, I'm going to do milliliters just so you can see, 50 and 50, total volume is 100 milliliters. Which, if you divide millimoles by milliliters, you are going to get, this is going to cancel the milli, and you're going to get 0.0167 molar. So that's PO4. What do we have left? Let's do the Na and the Cl. So we've got Cl minus concentration. We have 10 millimoles divided by 100 milliliters. And that's going to give us 0.1 molar. Okay, we did this up here to figure out Cl minus. I'm going to put little notes here. And we did this up here to figure out what was left of the PO4 minus. And we did this over here to calculate the well, it was also PO4. Now the Na is a little bit different because we have to start with 5 millimoles of the Na3PO4, and we've got 2 Na3PO4 in the equation going to 6 NaCl. So 5 times 6 is 30 divided by 2. This is 15 millimoles. And that's going to represent the Na plus ions. So when figuring out Na over here, here's our Cl. Let's do Na way over here, Na plus. We've got 15 millimoles divided by the total volume of 100 milliliters. and that's going to give us 0.15 molar for our Na concentration. So let's make sure that I have everything. I did Na, we did Cl, we've got Cu at 0, and the PO4. Okay, big problem. Let's move on. Finding the molarity of an acid. So that again, this is going to be using stoichiometry and a balanced equation. First and foremost, you always need to start with a balanced equation. So let's say we've got NaOH titrated with, as soon as you see this, you should be thinking some type of neutralization reaction. It's an acid plus a base. Acetic acid. And that's going to yield sodium acetate, which is a salt, and H2O. So this is all 1-to-1, nicely balanced already for us. So for our NaOH, we've got 0.25 molar, 20 mils, and that's going to give us 5 millimoles. And we know that we used 23.2 milliliters, but we don't know the molarity. Well, if it was titrated, and it was titrated to the phenolphthalein endpoint, which is when the indicator turned pink, you know that neutralization took place. So we can use stoichiometry. Since we have a monoprotic base, a monohydroxy base, and a monoprotic acid, we know that they're combining at 1-to-1. So if I have 5 millimoles of NaOH, then I know if I have 1 millimole of NaOH, in my balanced equation I also have 1 millimole of the acetic acid. So I'm just showing you that this was a 1-to-1 ratio. So this is going to leave us with 5 millimoles of the acid. So now we know molarity is equal to moles over liters. So I've got 5 millimoles over 23.2 milliliters. Milli cancels, which is going to give us this gives us approximately 0.216. So we will make it 0.22 molar. So we answered question 1 already, concentration. In this one, it says 10 mils of 0.5 molar NaOH is titrated with 23.2 molars of H3PO4 to the endpoint. Again, titrated with its neutralization to the endpoint. One thing that I need to make sure that I am aware of is that I now have my OH to H ratio is 1-to-3. So I have a monohydroxy base and a triprotic acid. So let's write a balanced equation. NaOH plus H3PO4 is going to yield Na3PO4 plus H2O. So I need 3 of these, 3 NAs, and I've got 1 PO4, 6 H's, so I need 3 here. 6 H's, 3 H's here, another 3 here, and then I'm balanced. So what do we know? We know that we've got 10 mils of 0.5 molar, which is going to give me 5 millimoles. And I've got 23.2 milliliters, and I don't know the molarity again. So I can use some mini Stoi. I've got 5 millimoles of NaOH. I have 3 moles in my equation going to 1 H3PO4. So my moles are going to cancel. And I'm going to be left with, this is moles here, 5 times 1 divided by 3, 1.67 millimoles. Molarity is equal to moles over liters, so 1.67 millimoles divided by 23.2 milliliters. And then I'm going to be left with 0.072 molar. And that's my answer. Alright, I think we've got a couple more problems left. Drawing near the end. So we have 0.523 grams of an unknown monoprotic acid, and it's titrated with phenolphthalein to the end point with NaOH. So whenever we don't know what something is, we know acids begin with H, and the A can be for the anion. So monoprotic would be just HA. If it were diprotic, it would be H2A. Okay, but I doubt we're going to see that. So we've got some unknown monoprotic acid plus NaOH, and that's going to yield NaA, because we don't know the anion, plus H2O. So A, if you want to write a note, equals your anion, which is your negative ion. So we have 0.523 grams of this, and we've got 22.5 mils of 0.103 molar. So let's figure out a couple of things. Well, if we've got molar and milliliters, we can figure out moles, right? So this is going to give us, well, millimoles. This is going to give us 2.32 millimoles of NaOH. What we can see based on this equation is that our HA to NaOH ratio is 1 to 1. So therefore, if I have 2.32 millimoles of NaOH, that's also equivalent to the millimoles of HA. So, what are they asking us to find? They want us to find the molar mass of the acid. So, we know that moles equals given mass over gram formula mass, right? This is what they're asking us to find. We know our grams, right? So if I rearrange to solve for an unknown here, I'm going to have GFM equals given mass times both sides by GFM divided by moles. So my given mass is 0.523 grams. We just said that if I have 2.32 millimoles of NaOH, that equals my moles of HA. But for agreement of units, we need to divide by 1,000, right? Because this is millimoles and we need moles. So I'm going to move the decimal 3 places to the left. So that's going to give me 0.00232 moles, or 2.32 times 10 to the negative third moles. So 2.32 times 10 to the negative third moles. Now I've got grams divided by moles, and I get 226 grams per mole, which is equal to, for my HA, there's my molar mass. Last two problems. Well, it's one problem, 2 parts. Again, always starting with a balanced equation. I've got 50 mils of 0.1 molar KMnO4. It's titrated to the endpoint with FeSO4. The solution is acidified. Okay, so a couple of things that stand out right away. KMnO4 and the Fe, and it's acidified. So I'm thinking my redox equations. So what I'm going to have to do first is balance this equation. What do we know? KMnO4 plus FeSO4. If I go all the way back to my chart, so I want you to turn, I'm going to do it with you, but I'm not going to turn the computer screen. I want you to go back to page 18. And I want you to look at your redox reaction prediction list. What you know here is that the Fe is +2. It's considered an important reducer because it's a metallous ion. 2 big metallous ions are going to be copper +2 and Fe +2. So that means that this is going to go to Fe +3 on this side. And what do we know about the MnO4? If you go all the way to the top of the important oxidizers, it says MnO4 minus, which is the ion here, in an acidic solution, and they said it was acidified, is going to go to Mn +2. Okay, so now we have an acidic solution, so we have to balance the equation using redox rules. Let's do the Fe first and get it out of the way. It's easy. We've just got Fe +2 going to Fe +3. So that you're only using to balance with an electron. And then we've got the MnO4 going to Mn +2. So I need to add 4 waters to this side, which means 8 H pluses to this side. So now I've got a plus 2 on the right. I have an 8 plus 8, 8 times plus 1, and a negative 1 gives me a net plus 7. So that means I'm going to add 5 electrons to this side, because a net plus 7 and a negative 5 gives me a net plus 2, which means I'm going to multiply this equation by 5, which is going to give me 5 Fe plus 2 going to 5 Fe plus 3 plus 5 electrons. Now these can cancel. So my final equation is going to be 8H plus MnO4 plus 5 Fe2 plus going to Mn plus 2 plus 4 waters and 5 Fe3 plus. Now, you might be wondering why I didn't bring in the K and the SO4, because basically they're not participating in the reaction and are irrelevant to answering the question. Because we really only want to deal with what's oxidized and what's reduced, because they're asking about the concentration of the Fe2 plus ions. That's it. So now that we have a balanced equation, let's see what we started with. We started with 50 mils of 0.15 molar, 0.1 molar KMnO4, which is going to give us 5 millimoles. So I've got 5 millimoles of the KMnO4. I have 1 KMnO4 in my equation, and that's going to 5 Fe2 plus moles. So 5 times 5, I'm going to have 25 millimoles of Fe2 plus. And you know that molarity, just keep this in mind, is equal to moles over liters. So there's my millimoles divided by my 20 milliliters. Gives me 25 divided by 20, which is 1.25 molar Fe2 plus. And that's my answer. Okay, I got a whole lot of editing to do. And that's the end of Chapter 4.